Okay, so let's start with the concept of an SR latch, right? So we are starting with an SR latch, and this is an active high latch which is constructed using NOR gates. We can do it using NAND gates, that will be an active low logic. So for now, let's deal with this. So this is the circuit diagram, what you can see. Now the function table is this, that 0, 0 is my no change state. So during 0, 0, whatever my previous state of Q and Q prime are, that will be hold. Now when I go and apply the set bit, my Q bit is set or it becomes 1. My Q complement bit is always the complement of Q, so it is 0 now at the moment. If I give 0, 0, this is hold. Exactly the previous set comes here, right? The previous whatever the output, it just holds that. Now if I give 1, 0, so I'm resetting the bit. You can see that the bit is reset. It is 0. So Q is what we are mainly dealing with. Q complement will always follow the opposite of Q, right? And similarly, now if we give again 0, 0, again this is hold. Again we give 1, 1. Now see, when we are giving 1, 1, we are asking it to both set the bit and clear the bit. So set means Q will be 1 and reset means Q will be 0. Now if you give both at the same time, the flip-flop doesn't, the SR latch doesn't know what to do. So what it does is it just gives you an indeterminate state which is denoted by X. So even though it's given 0, 0 here, a more better representation is X. It is indeterminate, we do not know. Now if you ask it to hold this indeterminate state, now we will get some output, but it may be anything but floating. So it might be 0, 1, it might be 1, 0. We don't know what is the output. It can be anything amongst these two. Of course, Q will follow Q complement, but what the exact output will be, that we don't know. So this SR latch kind of looks like this. This is what we represent it in the circuit diagram, right? Now, what we can do is, this is just the latch. So we are applying some S, we are applying some R, and when S and R are changing, we are getting some Q, we are getting some Q complement. Now, suppose you need it inside a processor. So processor runs on clock. So you would desire a clock signal and the SR latch to basically work on that clock signal. So how can we implement that? By using a circuit like this. So this is my latch, right? And this is using the NAND gate. So this is how the SR latch would look if it was made using NAND gate. And note that these are flipped, right? So 0 here means active high. So 0 actually represents 1 here, right? Contrary to what is done using the NOR gates where 1 is active high. So what is more important is not that. Basically we are supplying S and we are taking R and we are using NAND gate along with a clock cycle. What this means is that when clock is 1, correct? So suppose you are supplying some value of S, let's say 1. So if both are 1, then this NAND gate will take this, and what will be your output here? So 1.1 whole NAND. So this will be 1 not or 0. So when clock is 1, we do not get any output. Now when clock is 0, then you get 0.1. So it is 0 complement. So you get 1. Correct? So that is what is interesting, that the clock cycle basically flips this S, which means that this basically this goes from being an active low latch to an active high latch. So now you can see the behavior is once again preserved. So if we set reset, you can see that Q prime is 1, Q is 0, correct? Now if we set 0, 0, it holds. Now of course it is always when clock is 1. If clock is 0, nothing happens. Clock is 0, we do not know what is S and R. There is no change. Whenever clock is 1, then whatever we give, suppose S is 1, R is 0, then Q becomes 1, the bit is set, Q complement goes to 0. So that is how a SR latch can be made to work with a clock cycle. Now once again, 1, 1 is still invalid, and holding this state will also become an invalid thing. Now we can turn this into a D latch. What is a D latch? See, in the SR latch, there is a race condition which is this 1, 1. If you give 1, 1, the data is invalid. The SR latch doesn't know what to do. Now, if you take a signal D and you feed it like this. So if let's say you take D over here, you connect this to S and then you connect a NOT gate from D and you connect this to R, see, this condition can never happen. So if you give whatever value you set of D here, S will get that value and R will get exactly the opposite value always. So this condition is completely avoided. So this is known as a D latch. And that is how you can convert an SR latch into a D latch. And when this thing, using this basically, we can take a clock cycle. So if this clock wasn't there, this would be a latch. And if we apply this clock, that is where we get introduced to flip-flops. So D latch, we have seen here, this is how the D latch versus the D flip-flop works. So in the latch, if you don't give any D, then Q is not changed. If clock is 1, so basically if clock is 0, whatever value of D you give, Q does not change. If clock is 1, which means the clock is on the rising edge, and you give D is equal to 0, then Q is 0. So this data is simply passed down here. If clock is 1, if D is 1, then again this data gets passed on to Q. So basically whatever data you feed to D will get passed to Q on the rising edge of the clock. That is how this flip-flop works. Now, coming to the flip-flop. This is the same thing basically as the latch, as the flip-flop. So this is, I should not say this is a latch because I have given the clock cycle here. So this is how the positive edge triggered flip-flop basically works. So D0 is reset, so Q is 0. D1 is set, so this is 1. If this clock cycle was not there, if this signal was not required, if this was happening on its own, then this would have been a latch. But since we are requiring this clock cycle, this is what is known as a D flip-flop. So basically you give a data line and whenever the clock pulses, the Q value, the output value will reflect that data. Okay, so with that, we can also get what is called as a toggle flip-flop. Toggle flip-flop is an interesting case where if the toggle bit is 1, at the clock edge, Q gets complemented. So let's take a look at this. So suppose we are giving a clock cycle. We have a toggle bit and we have Q. So whenever the clock cycle is going to 1, suppose Q at this point was 0 before coming to this clock cycle. You set toggle to 1 and what happens is, see at this edge, so this is the edge at which we will be seeing. So if I draw a line, this is the point at which the flip-flop will see this signal and it will flip Q. So Q will go to be 1. See, Qn plus 1 is equal to Q complement if toggle is 1. Else Qn if toggle is 0. Now if I keep toggle 0 and let's say my clock pulses, so my Q, since it was set to be 1 here, this will continue to be 1 until let's say I again set the toggle 1 and after a few clock pulses, let's say at this pulse, my toggle bit is 1 is sampled, then right over here once again my Q bit will get flipped and it will start to become 0. So this is a toggle flip-flop. Whatever you set T, whenever you set T at that clock cycle, the output bit flips, and whenever you set T is equal to 0, the output bit is held as is. So this can be made using a D flip-flop, just we had seen, using some sort of a combinational logic. So this might be asked, this is actually a question, that let's say this is a random combinational block and this is a D flip-flop. So how can you turn this into a toggle flip-flop? It is easy. This combination logic is nothing but this gate, right? So if you use this XOR gate with T and Q and then you combine the output here, then you will basically get the combinational logic of this. So basically this is how you make a T flip-flop using a D flip-flop. Okay. Also there's a JK flip-flop. Now JK flip-flop is where it becomes a bit complicated. So there is two signals, J and K. And this goes to some combinational logic which controls Q and Q prime, and this is also feeding to D. Now what is that logic? We are not interested in at this point, but there are the following commands we can set. So either we can set a no change command, we can set reset, set, and complement command. So this is a new thing which we had seen earlier in the toggle flip-flop. So the JK flip-flop is basically combining the functionality of the toggle flip-flop and the D flip-flop. So we can set it, we can reset it, we can hold the state, but also we can complement it. So let's take a look at its table. So when jk is 0 0, then qn and qn, this is hold. So qn plus 1 is this. I think this will be complement. No, this just explains what is happening. So this is the state explanation. So qn plus 1 is qn. So qn plus 1 will be whatever the last value is. This is the last value of qn, that will be hold. Now 0 and 1, if you set k is equal to 1, this is considered as reset state. So whatever it was there, the d value will basically become 0. qn plus 1 will become 0. The output is 0. Now if you state j is equal to 1 and q is 0, this is known as the set bit. So the output becomes 1. The same as what we had learned earlier. Now if both is 1, where in the SR latch this was a race condition, since we have added extra combinational logic, this actually returns the complement of qn. So let's say earlier it was 1, then here the complement will return 0. So that is how we practically implement a JK flip-flop. So this is how the diagram looks like, the circuit diagram. So this is a D flip-flop. You take J and K, you AND it with, so J gets ANDed with Q complement. So you can see this line is tracing over from this point, and K gets complement, K gets AND with Q, and then both of this pass through an OR gate. That is what you get Y, and that is what you feed to the data line of the of the normal flip-flop, right? I forgot its name. This D flip-flop. So you feed this to the D flip-flop, and that is how you get the JK flip-flop. Once again, JK flip-flop also requires the clock cycle to work. We are not seeing the clock cycle as of now. Now qn plus 1, this is what is known as the actual, what can I say, the representative equation. This might be asked a lot of time, that qn plus 1 is equal to j dot qn complement plus k complement dot qn. Now try and do this for all of these. So for D flip-flops, for toggle flip-flop, all of these, try and writing this equation. Some of these are given here, like for D flip-flop, this is the characteristic equation, qn plus 1 is equal to D, simply at the next clock cycle. For toggle flip-flop, this is the characteristic equation. So this is kind of like maths, right, where you write a function and you show what the function will be at various values of inputs to the function. So that is more or less entire thing to do. Now timing diagrams are there. I don't think timing diagrams will come in this exam, but even then, this is what happens. So whenever the clock is pulsing, that is the point where the line will change. So that is the only thing you need to remember, that wherever this arrow is there, only then that so this t can change independently. So whatever input you are giving, that can change at whatever time, but the output will only change when the clock is pulsing, or a bit later, slightly delayed from the clock. That is the entire thing. I don't have anything more to say. So yeah, that is entire thing of combinational logic and flip-flops. Okay, there is another topic which is known as parallel load. So now using this flip-flops, we can basically implement registers, right? So comes the concept of shift register. So if you see here, if we connect multiple DQ flip-flops like this, right? Now if we give A is equal to some signal, let's say A is 1. So in the first clock cycle, this flip-flop holds the data 1. So here you get 1. Q you don't know, Q2 you don't know, Q3 you don't know. Correct? Now in the next clock cycle, this data is in this line. So this flip-flop gets the data 1. Now this flip-flop, again A is held at 1. So this flip-flop again samples 1. So Q is again 1. But now this flip-flop has also gotten 1. So Q1 is also 1. This is unknown. This is unknown. Again, when the next clock cycle pulses. So now if you change, suppose A is equal to 0. Then this flip-flop reads 0. So it becomes 0. This flip-flop reads this 0 line. Oh, so this does not have the time to read this as of now. So it keeps 1. Now this reads this 1 and it becomes 1 over here. So it becomes 0, 1, 1, and this is still undetermined. So that is how it happens. So every clock cycle, whatever data you're giving to A, this shifts across the flip-flops and the cycle continues. So you can see here that is happening. Now see, what is important is that the rising clock edge is whatever is happening. So in the rest of the clock cycle, we are not concerned. Whenever it's the rising edge, then only the toggle happens. Okay. Another thing is parallel load shift and parallel load serial shift. So this type of shifting is called as serial shifting, where you're giving a data and it is going one after the other. But you can basically expose these data lines over here using a multiplexer, and that allows you to parallelly load in the data. So the entire data, let's say you're having a parallel bus connected here, and the bus suppose gives 0 1 0 1, correct? Now this Q3, this will shift out this in exactly this order. So if you're giving 0 1 0 1, see, first it will give this 1, then it will give this data 0, then it will give 1, and then it will give 0. So whatever data you're feeding to these lines, from the highest bit to the lowest bit, this flip-flop will exactly give you that output on every clock cycle. So you can parallelly feed in data, use a multiplexer, and then get the serial data out. At the same way, what you can do is you can also feed in serial data, because this line is still exposed. Then it just works as this earlier shift register. And the final thing that we will do is, okay, that is entire thing. So this is a multi-level shift register. You can see that this entire thing works as a data line. So I3, 0, 3:0 is basically representing 4 bits of data. So there will be 4 bits of data, and this is how we do timing analysis in higher level digital electronics. We are not concerned with that over here. So that is more or less the entire syllabus of digital logic.